Welcome to Lecture 5 for Radiochemistry 702. This lecture is on nuclear force, structures, and models. This lecture will cover nuclear models and really emphasize the shell model. The main aspect of this lecture is to be able to use the shell model to determine the spin and parity, and then we'll move over to Nilsson diagrams to describe what happens if the expected spin and parity based on the shell model is not what's actually observed. The readings from this lecture are listed here. Chapter 10 in Nuclear and Radiochemistry, Chapter 5 in Modern Nuclear Chemistry, and Chapter 6 in Modern Nuclear Chemistry. Topics that we're going to go over, we're going to introduce the strong force primarily, and the strong force here shows the force that holds nuclei, the nucleus together. It's a very short-range force on the order of the diameter of a medium-sized nucleus. And it's fundamentally the force that holds the nucleus together. We'll introduce the term isospin. We'll talk about how nucleons can be explored independently. So in other words, try to treat protons and neutrons as the same sort of particle. Then we'll go on a review of nuclear potentials, and then talk about the shell model. So for nuclear force, we'll talk about with structure reactions and decay of nuclei, how there's a number of forces involved. And in this lecture, we'll primarily focus on the strong force. And we'll talk about some of the fundamental forces that exhibit exchange characters. The strong force has a very short range, on the range of a nucleon. And the nuclear force, the strong force, is attractive in very short distances, and is the real reason why there's dense nuclei. The force between two nucleons has two components, a spherical component and an asymmetric component. Let's consider a very simple nucleus with two nucleons. Deuterium, H2, it's got a proton and a neutron. It has a parallel spin of 3s. It can be in an excited state. The antiparallel is unbound. So in other words, we can look at these nucleons and we can almost consider them as electrons, where the differences between an electron could be a spin up and spin down. Fundamentally, with the strong force, we can do the same with nucleons. As was already stated, the strong force is charge independent. So, in this case, pairs of neutrons and protons, or proton-protons should have the same. So somehow, in order to evaluate a charge-independent force, one must remove the Coulomb repulsion from any energy calculations. This can be done by looking at nucleon-nucleon scattering or by mirror nuclei. And here's an example of some mirror nuclei, and these mirror nuclei are isobars with a number of protons in one nuclei equal the number of neutrons in another. So for instance, if we look at 23, we can have sodium 23 and neon 23 as mirror nuclei. As you can imagine, you can evaluate mirror nuclei for only fairly low A. As you go higher in A, you couldn't get a nucleus with more protons than neutrons. So what one could do with this is evaluate energetics, particularly looking at binding energy, and then compensating for the Coulomb energy, to try to evaluate a net nuclear binding energy for different nuclei with the same number of total nucleons. And this is shown here. So we have total binding energy, and here's the net Coulomb energy. And as we can see, imagine for something like tritium, there's only one proton, so the Coulomb energy from that would be 0. So for the other nuclei, we have Coulomb energies that are calculated based upon the number of protons in the nuclei. And what this shows, if we take the total binding energy and compare it with the Coulomb energy, we see that the net nuclear binding energy is very similar based upon the total number of nucleons in a given nucleus. And this can be used to show that protons and neutrons are actually two states, can be considered two states of the same particle. And actually this term is called isospin, and it's another parameter that can act to determine reactions based upon the strong nuclear force. And here's some data on isospin. It's a property of a nucleon where the proton can have a spin of 1/2 and the nucleon and the neutron spin of -1/2. Now a nuclear potential is where these nucleons can act together, form a nucleus, and then provide properties that we can observe on this nucleus. We've already talked a little bit about nuclear potentials, but these nuclei can be particles in a potential well. The nuclear forces describe the potentials. The well is small. And we also know that the well can stabilize nucleons. For instance, I can put neutrons into a nuclear potential, and they can remain stable. A free neutron is not stable. It decays. Also, the way I mix nucleons can be stable. For instance, I can put, if I have 2 protons, that's helium-2, that's an unstable nucleus. 2 neutrons is unstable. But if I have a proton and a neutron together, that's deuterium, that's a stable nucleus. And I can also imagine that with A of 3, I can get mixtures of protons and neutrons that are stable. However, 3 protons would be unstable. And this nuclear force within this potential, they act upon the nucleons in a uniform way. So protons that protons have this Coulomb repulsion that act to destabilize the nuclei. So that's why when we get more proton-rich nuclei, we tend to have excess neutrons to help minimize this Coulomb repulsion. So at low A isotopes, these light isotopes, symmetry is favored, where the number of neutrons is approximately equal to the number of protons. As we go higher, this isn't true. In some respects, the potential energy of 2 nucleons that can be unified in this potential are similar to some chemical bond potential energy functions. So that can actually be used as a model to help describe the behavior of nucleons in a potential well. These concepts and ideas that we've just discussed can actually be applied to the shell model. And we've already kind of hinted at the shell model where there's some experimental evidence. For instance, the ground state spin for all even nuclei is 0+. We've discussed magic numbers. So there are certain nuclei or certain states where there's enhanced stability for nuclei, which is pronounced in fission, for instance. There are some systematics on ground state spins for odd mass numbered nuclei, relationship between magnetic moments and their spins, and some of the properties of ground states of odd mass numbered nuclei can be determined from that odd unpaired nucleon. So it's as if if I have an odd A nuclei, all the nucleons are paired except for one, and that one unpaired single particle provides the properties for the nucleus. That's fundamentally one of the bases of the shell model. One of the other things with the shell model that can be derived is stability of nuclei based upon the number of neutrons and protons. One of the bases of the square well is the potential in which the nucleons sit. A simpler model is to describe the nuclear potential as a square well. A little bit more advanced is the harmonic oscillator, where you get a parabolic shape of the potential. With the harmonic oscillator, we get energy levels that are regularly spaced, shown here. And this is useful really for only low-lying energy levels. If by changing the nuclear potential, to a square well with rounded edges, as shown here, we enhance the stability of states near the edge of the nucleus, and we can take these, so we see a lowering of the energies, we see a splitting, and then this splitting goes even further when spin orbit coupling is applied. And this allows us to see where the magic numbers come from, where we have gaps in the energies between the levels, and these occur at 2, 8, 20, 28, 50, 82, 126. So the shell model is really the square edges and the spin orbit coupling combined. The shell levels are filled based upon their relative energies, and we can define the states by two quantum numbers, n and l, n being a principal quantum number, l being angular momentum. And unlike electrons, nuclear states can have a 1p, a 1d, a 1f, a 1g. So there's a variation in behavior of the shell model with the electron model. What we can do, when we look at these states, we know that there are some states which are degenerate. So we can group some energy levels together. Degenerate states, if I take 2 times n plus l, those with the same numbers, so n and l, so 1s, the n would be 1, the l would be 0. Those states with the same 2n plus l are going to be degenerate, and they'll be grouped together. As an example, if we look at this state here, which is composed of the 2s and 1d state, 2s, 2 times 2 plus 0 is equal to 4, right? Because the n number is 2, the l number is 0 from s. Where d, a 1d state, the n is 1, the l is 2, where s, p, d, right? So 0, 1, 2, the d is 2. So that's 2 times 1 plus 2 is equal to 4. Those two states are degenerate. We can see the same thing shown here, where we have the 1g, 2d, 3s, where all these equal to 6, and those levels become degenerate. And then when we have spin orbit coupling interactions, where we can split the angular momentum, where J equals L plus S. As an example for this, we could take the P states, where P is equal to 1. S can either be, the spin is either plus 1/2 or minus 1/2. So the splitting of the P states will either be a 3/2 or a 1/2 state. And this is split into a fourfold degenerate, for instance, in this case, a 1p 3/2, which is shown here, or a twofold degenerate 1p 1/2. And when we say a fourfold degenerate p 3/2, it means I can put 4 nucleons into that state. When I say a twofold degenerate 1/2, it means I can put 2 nucleons into that state. The other thing that we see is the gaps appear at the 1n quantum number. So see a 1s, a 1p, 1d, the gaps are here. 1f, the gap is here. 1g, the gap is between the two 1g orbitals that are formed. Same thing with the 1s, excuse me, the 1h. Even the 1i is at the lower, is at the gap that defines the shell, that defines magic numbers. And we see the 1j here defines the magic number of 184. So from these trends, from the quantum mechanics of the shells, we get a lot of properties that come out with the related to the shell model, particularly the magic numbers and how many nucleons can go into the different orbitals. So the nucleons fill the shells in the shell model from lowest to highest energy. And as we already discussed, an odd A nucleus with one unpaired nucleon will provide the property of the nucleus. It'll basically have some sort of even core with one unpaired nucleon. So whatever state that unpaired nucleon is, the spin of that state will define the spin of the nucleus. The parity will be based upon the orbital angular momentum. So S's, D's, G's, I's have even parity. P's, F's, H's have odd parities. For odd nuclei, where one odd proton and one odd neutron each contribute to the spin and parity, there's no universal rule, and we'll provide some examples of how you can estimate the spin and parity of odd nuclei. Here's our shell model, and here's some of the properties that come out from the shell model. The lowest level is obviously this 1s. It's a s1 half. Since L is 0, J is only equal to the L plus the S, so 0 plus 1 half. It only has the one value. It's shown here, and it contains two nucleons. So I can put two nucleons into the shell. For the proton side, I can put two protons. For the neutron side, I put two neutrons. These are the total number, and that's a magic number. So for the shell model, there's a component that is for the neutrons and a component that's for the protons. The next level, we get to the 1p orbital, which splits into the 3 halves and the 1 half. And that's shown here. And we see that for the lower lying 3 half state, we can put 4 nucleons in. The total amount of nucleons will be 6. So this will be either the 6 protons or 6 neutrons completely filling this shell. The P1 half, I can put 2 nucleons, total number of 8, and this is a gap where 8 winds up being a magic number. So something where I have 8 protons and 8 neutrons, which would describe oxygen 16, should be especially stable, from the nuclear component. We see the other shell closures at 20, 28, 50, 82, 126, and then 184. These enhanced abilities from the magic numbers correlate with these gaps in the shells. A few stable nuclei have both closed neutron and proton shells. They're very strongly bound relative to their neighbors. We can also call these doubly magic nuclei, and some examples are listed here. Helium 4, oxygen 16, calcium 40 and 48, lead 208. We can also find doubly closed, doubly magic nuclei that are unstable. Examples are given here, and particularly tin 132 being one of the driving force in the asymmetric fission distribution. So the other aspect of the shell model is here where we can see the number of nucleons, either neutrons or protons, that can fill a given shell, the total amount of nucleons at that given point that fill the shell, and then finally the magic numbers. So as an example, if I have a nucleus with 21 protons and an even number of, say, 20 neutrons, the 21st proton is unpaired. So that'll be, I can put 20 here. The 21st will go into this 1f7/2 level. So the property of the nucleus will be dictated by that unpaired nucleon in this level. We'll go over some examples. Let's consider lithium-7. 3 protons, 4 neutrons. The proton number is odd, so that's the odd proton is going to define the behavior of the nucleus. And we see that this one unpaired proton, the 3rd proton, lives in this 1p3/2 level, right? Because I can put 2 protons here, the 3rd one is here. So the spin and parity are based upon this unpaired proton. The spin, if it's 1p3/2, the spin should be 3/2. The parity is based upon the p state. It has an L value of 1, so the parity, that's odd, so the parity is negative. And as we see, lithium-7 is 3/2 minus, as predicted from the shell model. We see here, this is the state that it occupies, and the 1p3/2 correlates to 3/2 minus ground state. The excited state, shown here of lithium-7, is 1/2 minus. So the question is, if I have an excited state, I can either take the unpaired proton and excite it, or split one of the paired neutrons and excite one of those. It's much easier for the first excited state just to take the unpaired nucleon and excite it. So the unpaired nucleon would be living in this 1p3/2. The next state up would be the 1p1/2 state. We would expect the excited state of lithium-7 to have a spin and parity based upon the 1p1/2. So the spin would be 1/2. The parity based upon the angular momentum p. It's an odd L, so it should be negative parity. We would predict that it would be 1/2 minus, and that is what we see. The excited state's 1/2 minus, and it correlates with the shell model. We can now consider an example that's a little bit more complex than lithium-7. Let's consider nickel-57, which has 28 protons, 29 neutrons, so that odd 29th neutron, that's going to define the behavior of the nucleus. 28, 29th, that lives in the 2p3/2 orbital. p3/2, p has an angular momentum of 1, so negative parity 3/2. We would expect the spin and parity of nickel-57 to be 3/2 minus, and sure enough, the ground state is. So let's consider the excited state. The excited state is 7/2 minus, and if we look here, the 29th neutron is here. If we excite that, we go to a 1f5/2 level, which is what we see here. So F being negative, 5/2 state. So this also seems to correlate with nickel-57, 28 protons, by the way, magic number. So the nickel-57 is fundamentally one off from being a double magic nucleus. Another example, carbon-13, that's 12 protons, 6 protons, 7 neutron. The 7th neutron is unpaired. That 7th neutron, 6 will fill up here. 7th lives in the 1p 1/2 state. P, as we've already seen in the examples, is a negative parity, 1/2. We would expect the spin and parity of carbon-13 to be 1/2 minus, and it's true. Another example is with vanadium-51. The odd nucleon is the 23rd proton. 20 protons fit into this 1d 3/2, so I can put 3 into the 1f 7/2. 1 is unpaired. So F is also negative, so we would expect vanadium-51 to have a spin and parity of 7/2 minus. Now, the shell model isn't always correct. And as an example, let's consider barium-137. The 81st neutron is unpaired in barium-137. That would leave a hole, right, almost completely filled 82 nucleons. So 81 is the 1H 11/2 state. That would be 11/2 minus, and if you look at the table of the isotopes for barium-137, you see that it is actually 3/2 plus. Now there are some rules with this. Generally speaking, high spin states generally do not appear as ground states, so it's relatively rare to see something like an 11/2 minus as the ground state. And also the shell model is based upon a spherical nucleus. If the nucleus is not spherical, then the shell model will not actually predict the state. We'll discuss this in some later slides when we discuss the Nilsson diagrams. We've shown examples of determining the spin and parity for nuclei with one unpaired nucleon. We didn't go over with even nuclei because those are 0 plus for the ground state. Now, if we have a condition where we have an odd number of protons and an odd number of neutrons, so the spin and parity of the nuclei is determined by the coupling of each unpaired nucleon. One thing that we will see from a trend is that the spin values are integer values. And if we think about if we add two half integer values together, we should get a whole number. So we're going to get these integer spin values. Sometimes the coupling method isn't completely straightforward. One route to determine this is the use of the Nordheim number, where the Nordheim number is the sum of the spin and the orbital angular momentums. If we add the numbers together and the Nordheim number is even, then the spin is the difference between the two numbers, the absolute value of the difference. If the Nordheim number is n, we have two numbers that are possible, either the absolute value of the sum or the absolute value of the difference of the spins of the two states that are occupied by the unpaired nucleons. The parity is from the sum of the angular momentum states, the L states. If that sum is even, it's positive parity, and if it's odd, it's negative parity. We'll go over some examples to show how the Nordheim number works. For an example of the Nordheim number for an odd nucleus, let's consider chlorine-38. Chlorine-38 has 17 protons, 21 neutrons. 17th proton is going to live in this 1d 3/2 state. So the L is D, right? So D is 2, S being 0, P being 1, D being 2. And J, the spin, is 3/2. The 21st neutron, there's 20, 21, is here in the 1F 7/2 state. So L is 3 for the F state, J is 7/2. So the Nordheim number is just 2 plus 3/2 plus 3 plus 7/2, that's equal to 10. That's an even number, so the spin is just going to be the absolute value of the difference between 7/2 and 3/2. 7/2 minus 3/2 is 4/2, the spin is 2. The parity is from the L's, so that's 3 and 2. The L is 5, negative parity. the spin is 2, the parity is minus. We expect chlorine-38 to have a spin and parity of 2 minus. If we consider another example of aluminum-26, this is a nucleus with 13 protons and 13 neutrons. So this 1d 5/2 would be filled to 14, so there's a hole, there's one less, there's one missing spot for each the proton and neutron shell. So each particle, unpaired particle, has the spin of 5/2 and an orbital angular momentum of d of 2. So the Nordheim number is 5/2 plus 5/2 plus 2 plus 2. That's equal to 9. That's an odd value. So the spin is going to be the absolute value of the sum or the difference of the spin values. Each spin value is 5/2. So 5/2 plus 5/2 is 5. 5/2 minus 5/2 is 0. We would expect the spin to be either 5 or 0. The parity, each spin state is 2. 2 plus 2 is 4, is even. So the spin's either going to be 0 plus or 5 plus, and the actual value is 5 plus. So here's an example with the odd Nordheim number where you get a choice of answers to evaluate. The main assumption of the shell model is that nuclei are spherical. If one applies a particle model and discusses nuclei as particles in collective motion, one can come up with shapes that are non-spherical. Nuclei can have shapes such as prolate, shown here, or oblate. The prolate, the polar axis is greater than the equatorial diameter, and the oblate is opposite. Evaluation of these axes, so the axes that are defined here, shown here, the prolate nucleus, or the similar ones in the oblate. So the oblate, this x would be larger than the z, whereas it's opposite for the prolate. We can use that to define the deformation parameter. There's a term shown here, an expansion of this delta term. And the delta term is just nothing more than the difference between the axes divided by the root mean square of the axes. So there's a way of evaluating the deformation parameter in terms of the nuclear shapes. This changes the shell model to something that's shown here. This is called a Nilsson diagram. It's an expansion. You can think of it as an expansion of the shell model, where at 0 deformation, at that point, we have what we see in the shell model. If we start to go oblate, we get splitting occurring, so the levels change. We can basically now only put 2 nucleons into each of these levels. Or if we go prolate, as shown here, the splitting goes in the opposite direction. The key to this is that I can take a spherical model, and then by having the nuclear shape change from prolate to oblate, I can have a different spin and parity. So for instance, if it's spherical, this state represents the F7/2 state, so I can put 8 nucleons into this state. In a spherical state, as I'm filling up, all the odd nucleons, all the unpaired nucleons, would have the spin of 7/2, and the parity SPDF, so it would be 7/2 minus. However, if we measure a state that is not 7/2 minus, you can get an idea, you can provide an idea of the deformation of the nucleus. As we see, if it's deformed in an oblate parameter, the spins will be, the higher spins will be of lower energy, and the opposite is true for prolate. This deformation parameter is shown here, and the oblate nucleus will have a negative deformation parameter, and the prolate nucleus will have a positive deformation parameter, and a spherical nucleus, the deformation parameter will be 0. So fundamentally, what we can do from a very simple point of view is use a Nilsson diagram, evaluate what's the measured spin imparity, and if it varies from what we see with the shell model, we can make a prediction that we should see a nucleus of a given either oblate or prolate shape based upon the observed spin. Let's go over some examples for that. So let's consider iodine 127. It's a stable nucleus. Here's the Nilsson diagram for the protons of Z between 50 and 82. For iodine 127, it has 53 protons. That's the unpaired. From the shell model, we would expect the spin to be 7/2, the parity to be plus. The measured spin imparity for iodine 127 is 5/2 plus. So the deformation parameter should show 5/2 with an even L value. If we go to where the nuclei can live, if it's a spherical nuclei, it would be in the 1G 7/2. If it's a prolate nuclei, so a positive deformation parameter, the orbital should be occupied as shown by the blue arrow, and that should be in a 3/2 orbital because it's 53. So the 50 would be what was defined by the 1G 5/2 over here. 51, 52, 53 here. We actually see that for the oblate nuclei, it would be in this 5/2 shell. 50 would be here. 51, 52 would be in the 7/2. 53 would be in the 5/2 shell. We see that the spin and parity of iodine 127 is 5/2 plus. Based upon this Nilsson diagram, we could say that the nuclear shape, if the spherical is here, oblate is negative deformation parameter, prolate is a positive deformation parameter. The spin of 5/2 for the 53rd proton indicates that this nucleus is deformed with an oblate shape. We can do another example for potassium isotopes. Let's consider odd A potassium isotopes. So the unpaired nucleon is from the proton. Potassium has 19 protons. From the shell model, the 19th proton is living in this 1D 3/2 state. So we would expect a spherical potassium isotope to have a spin of 3/2 and a positive parity. If we look at potassium 47, it has a spin of 1/2, positive parity. So we would see that the 19th nucleon could be unpaired in this orbital or in this orbital. If it's 1/2, we know it's in this orbital. Here's the spin of 1/2. This 2, 0, 0, the 2 indicates that it's in the D state, so it's a positive parity. This shows that potassium 47 is an oblate nuclei because it has a negative deformation parameter. Another important concept discussed in this lecture is the use of the shell model to determine spin and parity. And we discussed that the spin and parity is determined by unpaired nucleons in the nucleus. all even nuclei. There are no unpaired nucleons, even number of protons, even number of neutrons. All even nuclei have ground state spin in parity of 0 plus. If we have an example of a nucleon with one nucleus with one unpaired nucleons, we can use the shell model to evaluate what should be the spin in parity. An example, titanium-49, the 27th neutron is the unpaired neutron, and in the shell model that lives here in this shell, which is the F7 halves, so the spin is 7 halves, F is 3, that is odd, so the spin is 7 halves and the parity is minus. If you examine the chart of the nuclides, you'll find that titanium-49 is indeed 7 halves minus. Another example, indium-113. The 49th proton defines this element, indium, that lives here. It's a G 9 halves. 9 halves is the spin, G is 4, so it's 9 halves plus. If you go to the chart of the nuclides and you see, you look up indium-113, you'll indeed see that spin and parity are 9 halves plus. This also indicates that these nucleons are spherical, since the shell model is used to evaluate and is based on spherical nuclei. Another important concept that was discussed in this lecture are nuclear shapes. So what are some examples of nuclear shapes? Well, as we described the shell model, there's spherical nuclei, but there are also nuclei that deviate from being spheres. One example is a prolate nucleus, and this is that the polar axis is greater than the equatorial axis. The other nuclear shape is an oblate nucleus, in which the polar axis is shorter than the diameter of the equatorial circle. And how does the shell model, how does this change with this deformation going from spherical to either prolate or oblate? Well, we go from using the shell model, which is shown here right along this line. As it changes, we go to our Nilsson diagram, and these states radically change. If you've taken inorganic chemistry, you've seen tsunami-Tugano diagrams, you'll see the same sort of behavior. And what we can see from this is that oblate nuclei are going to tend to lie on this side of the line that defines the spherical nuclei. So on the left side will be oblate, and the prolate will land on the right side. Right, those examples for the Nilsson diagrams, they can get very complex. However, from the very fundamental aspect, you should be able to understand if you see a variation between the shell model and what's measured, that it's a deformed nuclei. And for simple cases, you should be able to answer whether or not a nuclear shape is oblate or prolate. You should be able to talk about some of the concepts behind the shell model and infer from deviations in spin and parity based upon the shell model some information about the nucleus.
When you have completed this lecture, please comment on the blog and respond to the Lecture 5 quiz.